Have you ever noticed how your phone or your laptop just seems to get slower over the years? Well, I'm here to tell you it is not just in your head. The tiny components inside that make them so fast are literally physically wearing out. But now, for the super powerful AI chips in our newest gadgets, there's a brilliant new software idea that's fighting back against time itself. Let's dive in and see how it works. Yep, you heard that right. Those incredibly complex neural processing units, or NPUs, the special brains that power everything from your camera's slick photo effects to your voice assistant, they are on a countdown timer from the very first moment you power them on. And trust me, when that timer starts to run out, the results are not pretty.
So, what is actually happening deep down inside the silicon? Well, it all comes down to the fundamental building blocks of, all modern computing.
Okay, so inside every single chip, you've got billions of these microscopic switches called transistors. A good way to think of them is like tiny little paths for electricity. Every single calculation sends a jolt zipping through them. And just like a path in a forest, the more you use it, the more it wears down. This is especially true for an AI chip, which runs hot and works incredibly hard. This whole process, this physical wear and tear, well, that's what engineers call transistor aging. Now, this slowdown isn't just about your favorite app opening a half-second slower. For a high-precision AI chip, a transistor that's even a little bit too slow can set off a whole cascade of what are called timing errors. Suddenly, the chip's perfectly synchronized dance of calculations just falls out of step. And when that happens, it starts making mistakes. Tiny, tiny mistakes, but absolutely critical ones. And wow, this chart right here shows you just how catastrophic those little mistakes can be. It shows what happens to the accuracy of a few different AI models as the chance of a single bit flip error, that's a 1 accidentally flipping to a 0, goes up. I mean, just look at that drop. An error rate of just 0.05% can take a super powerful AI model and make it almost completely useless.
So, you might be asking, how have engineers been dealing with this problem until now? Well, the traditional solution is a bit like using a sledgehammer to crack a nut. I mean, it works, kind of, but it is incredibly inefficient.
So the old method is to build in something called a timing guard band. Basically, what they do is intentionally slow the chip down from day one, leaving this huge performance buffer just to account for the slowdown that's going to happen over its life. The supercar analogy is perfect. It's like buying a machine that can go 200 miles an hour, but you're forced to drive it at 40 for years, just in case one day it might lose a little power. It's so wasteful. And we're not talking about a small amount of waste here. To guarantee that 10-year lifespan, chip designers have to throw away a whopping 23% of the chip's potential performance right out of the box. You are paying for speed and power that you literally never get to use, all because of this brute force fix for aging. But this is where things get really, really cool. Some researchers asked a completely different kind of question, which led to a way more elegant solution, one that fights a hardware problem with software. I mean, think about it. Instead of just crippling the hardware from the very start, what if we could use software to intelligently adapt the physical changes happening in the chip over time? What if we could keep that supercar running at full speed, but just, give it slightly easier roads to drive on as it gets older? And that is the core idea behind this technique, called reliability-aware quantization. It's a method that doesn't touch the hardware at all. Instead, it dynamically changes the math that the AI is doing, making the problem simpler and faster to solve as the chip itself gets physically slower. Just think about doing math in your head for a second. Which one of these is easier, 187 times 241 or 180 times 240? The second one, right? Of course. By rounding the numbers, you make the problem way simpler and much faster to figure out. While quantization does the exact same thing for the AI, it just reduces the precision of the numbers it's working with to speed up the calculations. See, for an AI, getting a good enough answer really fast is often a lot better than getting a perfect answer too slow. So this all builds into this beautiful, elegant feedback loop. First, the chip gets older, its transistors slow down. Then the software sees this happening and automatically increases the level of quantization. It makes the math just a little bit simpler. That simplification gives the chip a speed boost. And the best part, that speed boost perfectly cancels out the physical slowdown from aging. The result is the chip just keeps running at its original speed. Okay, so what's the catch? There has to be a trade-off, right? And yes, there is. But it is an incredibly smart one. The system basically trades a tiny, almost unnoticeable amount of precision for a massive, massive gain in long-term performance. And the results, they're just stunning. Check out this table. It shows the speed of one of these AI chips over 10 years. A standard chip, without that clumsy guard band, gets 23% slower. But with reliability-aware quantization, the speed stays at or even better than its day one performance for a full decade. No slowdown at all. So what's the price for a decade of full throttle performance? This is it. That's the trade. On average, after 10 years of this adaptive math, the accuracy loss was a mere 3%. You sacrifice just a tiny sliver of perfection to completely solve the aging problem. What an incredible trade-off. So you see, this isn't just about making our chips last longer. This technique gives us a true trifecta of benefits that could totally change how we design and use these high-performance chips from now on. Okay, so let's just recap the big wins here. First, you get 23% more performance right from day one because we can finally ditch that wasteful guard band. Your AI just runs faster, period. Second, you get a device that stays fast, losing only about 3% accuracy over a decade. And third, and this is a huge bonus, because simpler math takes less effort, this technique also cuts energy use by an average of 46%. That means longer battery life for you. It's faster, it lasts longer, and it's more efficient. It's the whole package. And maybe the most brilliant part of all is summed up perfectly in this quote from the researchers themselves. This is a pure software fix. It doesn't require us to redesign the actual chip, which is incredibly expensive and takes forever. It's a solution that can be applied to chips we already have and ones we're designing for the future, making them all fundamentally better. And that just leaves us with this one fascinating thought. This whole solution is built on the idea of, well, aging gracefully, of accepting a tiny bit of imperfection to get huge benefits in performance and longevity. It really makes you wonder, doesn't it? What other unsolvable problems in technology or even elsewhere could we tackle with a similar, smarter trade-off?